And now for the philosophical and cultural apex of your otherwise meandering week. This is Physics 121 lecture. In this chapter, we are going to discuss the ideas of circular motion and Newtonian gravity. To introduce circular motion, let's think back to chapter 2. We introduced the concept of this quantity called acceleration, and we defined acceleration as the rate of change of velocity with respect to time. So what that means is if an object is accelerating, that implies its velocity will be changing in some manner. Later on in chapter 3, we learned about vectors. A vector is a type of quantity that has both a magnitude and a direction associated with it. The magnitude of velocity is what we call speed. That's basically how fast you're moving. And the direction of the velocity vector is whatever direction you happen to be moving in. Therefore, we could conclude that if an object is accelerating, either that object's speed is changing or that object's direction of travel is changing. In chapter 2, we really only considered acceleration as a change in speed, but if you think about circular motion, if an object is moving in a circle, its direction is continuously changing. If James Bond is strapped to a giant wheel, and we could pretend that wheel is spinning counterclockwise, when James Bond is at the top of the wheel, he will be moving to the left, and then the wheel spins him around. When he's at the bottom of the wheel, he'll be moving to the right. Even if he is moving at a constant speed, he has the same meters per second at all times, he still will be considered to be accelerating because he is changing his direction of travel continuously as he goes around the wheel. Now, when we talk about circular motion in this chapter, we will first assume that speed is constant. We will learn some things about how to think about circular motion, what's going on. We will connect the acceleration associated with circular motion to Newton's second law. And then after we talk about that, we will relax the assumption of constant speed and look at circular motion when you're moving in a circle and you can be speeding up or slowing down. So to begin talking about circular motion at constant speed, if I have an object that is traveling around in a circle, as I said, even though that object has a constant speed, which is our assumption for the moment, that object is still going to be considered to be accelerating because as it moves around in a circle, its direction of travel is continuously changing. And this acceleration, when you move around in a circle at constant speed, is known as centripetal acceleration. So here I have an object that is moving around in a circle, and I could say that this object is traveling in a circle of radius r. The distance from the object to the center of the circle about which it's moving is just a radius r. And this object right now is moving in a more or less upward direction. The direction of travel is changing, but we are assuming that the speed at which it travels is constant. Now, acceleration itself is a vector. To fully specify the acceleration vector, we need to specify both the size or the amount or the magnitude of the acceleration, and we need to specify the direction of the acceleration. So the magnitude of this centripetal acceleration is given as v squared over r, speed squared divided by the radius of the circle, and the direction of the centripetal acceleration is inward towards the center of the circle. Now, if you think about that for a moment, that implies that if an object is moving around in a circle, the direction of the acceleration can be changing because right now the direction of the acceleration in the way this picture is shown is more or less to the left. But later on, this heavy object is going to be near the top of the circle and the acceleration will point downward. And then later on, the heavy object will be over here on the left and the direction of the acceleration is going to be to the right. Even though the object is moving around, the direction of acceleration in terms of up, down, left, right, or direction of acceleration in terms of x and y is continuously changing. we always have a well-defined notion of inward towards the center of the circle. And the direction of centripetal acceleration, the direction of the acceleration when your speed is constant, is always going to be towards the center of the circle. Two other ideas that you will see in this chapter. These ideas are not as important as centripetal acceleration, but you will come across them, are the ideas of period and frequency. Period in physics, you could think of that as the amount of time it takes to complete one cycle. And this is somewhat of a general statement. In the case of an object swinging around in a circle, that is basically saying how many seconds does it take the object to move around once around the circle. Frequency is a concept that is very similar to period, but frequency is the number of cycles per second. So period is measured in seconds. Frequency will be measured in 1/seconds or inverse seconds. The SI unit of frequency is the hertz. So if I say that this heavy object travels 5 times around the circle every second, then I would say the frequency of this heavy object is 5 hertz. And the period of this object, the amount of time it takes to go around the circle, will be 0.2 seconds. If you think about the concept of period and frequency, you could convince yourself that these quantities are related, as period equals 1/frequency. Now, previously I said that if you are going to talk about the distance an object travels, you should be using that equation x equals x initial plus v initial t plus 1/2 at squared, because there is the possibility that that object is speeding up or slowing down. But if you think about it, as long as speed is constant, then we could say speed could be written as distance over time. And for circular motion, I could write the speed as being 2 pi r over the period. 2 pi r is the distance once around the circle, the circumference of a circle, and t is the period of motion, how long it takes to go once around the circle. So, as I said, as long as the speed is constant, we can say that the speed is 2 pi r over the period. Now, I want to be very explicit. If speed is not constant, then we need to account for an object speeding up, slowing down, and we cannot use this relation. The circumference, as I said, in this case is the distance traveled, which is one loop around the circle. Let's now take what we know about centripetal acceleration and connect it to forces. In chapter 4, we talked about forces by first saying, if I want to get something to accelerate, what do I do? And we thought about it and said, well, to get something to accelerate, you have to give it a push. If an object is accelerating, there must be a net force on it, and that is from Newton's second law, F net equals ma. Now, as I said before, throughout this slide, we are assuming circular motion at constant speed. Later on, we will relax the assumption of constant speed and talk about circular motion when your speed might be changing. So, if I am moving around in a circle at constant speed, that means that my acceleration has a magnitude of v squared over r. And therefore, I could say the net force on me must be m times v squared over r. All I'm doing is I'm taking what I know about the magnitude of my acceleration and plugging it into Newton's second law, and now I could talk about the magnitude of the net force acting on me. The direction of centripetal acceleration is always inward towards the center of the circle. If I look at Newton's second law is a vector equation, and I notice that because mass is a scalar quantity, the direction of the acceleration will always be parallel with the direction of F net. In other words, if acceleration is always going to be inward towards the center of the circle, then F net must also always be inward towards the center of the circle. Notice that throughout this discussion, we did not talk about the forces that are causing this centripetal acceleration. I feel in the previous chapter, we would be given some forces, whether it was tension or friction or gravity or whatever, and then we would add the forces like vectors, and then we did some vector equations to determine the direction of the acceleration. I feel in this chapter, when we talk about centripetal acceleration and centripetal force, we're doing the opposite of that. We are saying, if I know I'm moving in a circle at constant speed, that tells me the direction of my acceleration is inward towards the center of the circle, and the magnitude of the acceleration is v squared over r. Because the direction of the acceleration is in towards the center of the circle, that tells me the direction of F net. So in a way, we're doing the reverse of what we did with the previous chapter. I did not say anything about the nature of the forces that are causing me to move in a circle, but I do know what direction they all have to add up to. And again, remember that F net is the sum of all the forces acting on an object. So if I have tension and gravity and friction, but at the end of the day, if that object is moving in a circle at constant speed, I know all of those forces have to add up in such a way that the net force always points inward towards the center of the circle. So as a thought experiment, think about this question. Suppose you have a kid that is whirling a stone in a vertical loop like shown. Pause the video, think about this. At what point is the tension in the string going to be the greatest? Point A at the top of the loop, point C at the bottom of the loop, or point B at the side of the loop? So the answer to this question is point C. To see that, let's draw the forces and the acceleration acting on the stone. At point C, gravity is going to be pulling the stone downward. The tension force will be pulling the stone upward. And there are no other significant forces acting on the stone. So the force of tension and the force of gravity have to add up such that the acceleration is v squared over r upwards. If I, on the other hand, look at the forces on the stone when the stone is located at point A, the gravity force and the tension force have to add up, create an F net such that when I apply F net equals ma, the acceleration is v squared over r downward. So the tension on the stone will be at its greatest when the stone is at the bottom of the loop. Up to this point in this lecture, we considered the motion of an object moving around a circle at constant speed. We made a statement about the magnitude of that object's acceleration. We made a statement about the direction of that object's acceleration. And then we took what we knew about the object's acceleration, we looked at it in the context of Newton's second law, and we were able to make a statement about F net, the sum of all the forces that keep that object moving in a circular path at constant speed. Now let's investigate what happens to the acceleration of an object moving in a circular path if we relax the assumption of constant speed. Before I talk about that acceleration, I first want to mention the notion of the radial and the tangential direction. If you think about how we approach problems previously in this course, you would read a problem, you would draw a picture of that problem, and then you would set up your x and your y axis. Usually you would choose the x-axis to lie horizontally, you would choose the y-axis to lie vertically. This was not the choice for every problem you encountered, but it was a convenient choice for most of the problems you encountered. And once you set up your x and your y axes, you would just leave them and they would be the same throughout the entire problem. Very often when we consider objects moving in a circular path, it is more convenient to consider the radial and the tangential directions instead of the x and the y directions. The radial direction is defined as the direction towards and away from the center of a circle. The tangential direction is defined as the direction around the circle. Now, if you think about it for a moment, you could convince yourself that the direction that is the radial direction and the tangential direction will continuously be changing as your object moves around the circle. If the ride is moving in a counterclockwise direction around this loop, then the person in the car right here, at this instant, the radial direction is downward and the tangential direction is to the left. But as the ride proceeds, when the person is over here, now the radial direction, the direction towards the center of the circle, will be to the right, and the tangential direction will be downward. So unlike the x and the y directions that we used previously, the radial and the tangential directions will continuously change as your object moves around a circular path. However, similar to the notion of the x and the y directions we considered earlier, the radial and the tangential directions will always be perpendicular to each other. Another way of thinking about radial and tangential direction is the tangential direction is always going to be parallel to the velocity, and the radial direction will always be perpendicular to an object's velocity as it moves around its circular loop. When we considered vectors in previous chapters in this course, we were considering some type of mathematical object that has a directionality associated with it. If I considered the acceleration vector, I could think about the acceleration vector as having an x and a y component. Now, if I'm not using x and y as my directions, if I'm talking about the radial direction and the tangential direction, I can still consider the acceleration vector as a whole to have a radial component and a tangential component associated with it. The radial component of the acceleration vector is the component of the acceleration vector that causes a change in direction. The radial component of an object's acceleration is v squared over r, and it is directed towards the center of the circle. If you are right now wondering to yourself, what is the difference between this radial component of acceleration and centripetal acceleration we mentioned earlier in the slides? The only difference is when we talked about centripetal acceleration, we said speed is constant. Now we are allowing speed to be changing. So if my object is moving faster and faster, the radial component of my acceleration will become greater and greater as v increases. So regardless, at any moment in time, if I have a well-defined notion of speed, I can talk about the radial component of an object's acceleration. The tangential component of an object's acceleration is the component of an object's acceleration that causes a change in speed. And this is given as delta v over delta t. Notice that tangential component of the acceleration looks very similar to the way we defined acceleration back in chapter 2 as the rate of change of velocity with respect to time. So AR is the acceleration that causes a change in direction. ATan is the acceleration that causes a change in speed. AR and ATan are components of the total acceleration vector given by a vector. Now, if I think about acceleration, I can think about acceleration in terms of its components AX and AY. But for these problems, it is more convenient to think about the acceleration vector in terms of its components AR. The magnitude of AR is given by v squared over r. And ATan, the magnitude of ATan given as this. Because acceleration is a vector, it will have a magnitude associated with it. Previously, we would say the acceleration vector is related to its components by the Pythagorean theorem. And that statement still holds true here. Only now my components of acceleration are the radial component and the tangential component. But I could still apply the Pythagorean theorem to the acceleration of this object to say the total magnitude of the acceleration is AR squared plus ATan squared. So the acceleration of an object moving in a circular loop at non-constant speed is basically the exact same picture as the acceleration of an object moving in a circular path at constant speed, only when we considered centripetal acceleration constant speed, a tan was 0. Now we are allowing a tan to be non-zero, and the acceleration vector as a whole will not necessarily point towards the center of the circle. It will point a little bit in front of the object that is moving if the object is speeding up. It will point towards the center of the circle but behind the object if the object is slowing down. If you think about it, the a tan will be the component of the acceleration that is parallel to the velocity, and this is the component of the acceleration that causes a change in speed. And AR is the component of the acceleration that's perpendicular to an object's velocity. And this is the component of the acceleration that causes a change in direction. In the next video, we are going to go through some example problems of these concepts.